Hey everyone, welcome back to the channel. We are continuing our OpenStack series, and today we are tackling one of the most critical parts of any cloud: storage. Storage that must deliver performance, resiliency, and advanced features like volume management, thin provisioning, snapshots, cloning, and copy on write. Without this, OpenStack cannot spin up VMs quickly, manage images efficiently, or survive hardware failures gracefully. That's where Ceph comes in. Ceph isn't just storage. It's a highly scalable, self-healing distributed system that checks every box OpenStack needs. It delivers the speed for workloads, the resiliency for uptime, and the features for true cloud flexibility. In this episode, we'll dive into Ceph and actually build a 3-node cluster from scratch. Then, I will show you how to connect storage to a client device, create volumes, snapshots, and clones, and even demonstrate how Ceph keeps your data available when hardware goes down. I'm Philip, and if you are ready to see storage done the cloud-native way, let's get started. When we talk about cloud, systems need to store everything: OS images, applications, user data, mountains of it. And the challenge isn't just capacity, it's speed, reliability, and efficiency. OpenStack, because it manages huge pools of compute, puts incredible demands on its storage. Think about it: attaching storage to potentially thousands of VMs, spinning up new virtual disk instantly, storing and cloning massive OS images efficiently, ensuring data is always available even when hardware fails. These aren't nice-to-haves. They are absolute musts. You need a storage system that is dynamic, elastic, and incredibly resilient. Object storage is great for massive unstructured data, and file storage works well for shared workloads. But when the task is giving every VM its own fast, reliable disk, that's block storage. And that's the backbone of OpenStack's storage model. What is block storage? Instead of storing data as files in a hierarchy, block storage works with raw uniform chunks of data called blocks. The best analogy is this: block storage gives a virtual machine a blank hard drive. The VM's operating system can then put its own file system on top, like ext4, XFS, or NTFS, and control it completely. That's what makes block storage so powerful for things like operating systems and databases, where speed and flexibility are essential. In the cloud, these virtual disks are often delivered over the network using protocols like iSCSI, Fiber Channel, or Ceph's Rados block device, RBD. To the VM, it just looks like a local drive, but it's actually coming from a distributed fault-tolerant cluster. And that's exactly where Ceph shines. It doesn't just provide raw block storage. It supports thin provisioning, so virtual disks only take up space when data is actually written. It can create snapshots and clones instantly, making it possible to deploy or recover virtual machines in a second. And with copy-on-write efficiency, multiple machines can share the same base image without wasting storage. And this is exactly what OpenStack needs. OpenStack makes full use of these capabilities. With Ceph as its backend, OpenStack gets block storage that isn't just fast, but also resilient and massively scalable. Exactly what cloud infrastructure needs. Before we start building our cluster, let's understand the 3 main players that make Ceph work. First, we have monitors. These are the brains of the operation. They maintain the cluster map. That's the central point where the cluster state is stored. To ensure a clear majority vote, called the quorum, you need an odd number of monitors. This prevents the dreaded split brain problem, where different parts of the cluster disagree on what's true, which can lead to data corruption. When Linux client tries to mount a block device, the first thing it does, it checks in with the monitor. It grabs a copy of the cluster map, so it knows exactly how to find its way around. Then, when the client needs to read or write data, it uses the cluster map and applies the crash algorithm to pinpoint which object storage daemon actually holds the data. From there, the client connects directly to the right OSD, no middleman required. Which brings us to our second key player, the object storage daemons, OSDs. If the monitors are the brains, then the OSDs are the muscle. They do the heavy lifting, storing the data, replicating it, rebalancing it when needed. Each OSD typically manages a single physical disk, and they expose a network API so clients can talk to them directly. The more OSDs you add, the more parallel reads and writes you unlock. That means better performance, no bottlenecks, and a system that can scale almost endlessly. Finally, we have the managers. Managers gives you a window into the cluster health and performance. They run the web dashboard, collect metrics, and basically act as the control tower. We'll be setting up a 3-node Ceph cluster, which is the minimum required for true high availability. Each server will be running Ubuntu 24.04. All Ceph services will be running inside Docker containers, so we'll need Docker installed and ready to go. For storage, our cluster will use a total of 6 disks, that's 2 disks per node. This setup provides a solid starting point for a small but reliable Ceph deployment. The more disks you have, the better performance you can get, as data can be written and read in parallel across more drives. Also, a large number of disks result in more even distribution of data, which helps prevent hotspots, where some disks are utilized more heavily than others. Also, if the disk fails, Ceph must rebalance the data. It's much faster with more disks. The general rule is the more disks the better. We'll start with disabling swap. To make this change permanent, I will comment it out from the file system table. Ceph is designed to manage memory aggressively, and to ensure predictable behavior, we don't want it to start swapping. Then let's install Ceph ADM, a powerful tool for managing and deploying Ceph clusters. It is the officially recommended method for installing and managing Ceph clusters. Alright, with Ceph ADM installed, let's go ahead and bootstrap our cluster. During the bootstrap, we need to tell Ceph which IP address to use for the monitor service. Since we are on the first node, Ceph1, we'll use its IP. We'll also provide the cluster network range and some credentials for the Ceph dashboard. Our first Ceph node is ready to go. All the services are already up and running as Docker containers. Next, we need to configure SSH access so that Ceph can talk to other nodes in the cluster. Ceph requires passwordless SSH as root in order to manage and deploy daemons. To set that up, we'll copy the Ceph public key to the other 2 servers. Now, here's the catch. Ubuntu won't let us copy keys directly into the root account. To work around it, we'll jump onto node 2, create the SSH folder for root, set the right permissions, and then append our public key into the authorized key file. We'll repeat the same process on node 3. I will create the SSH folder and plant the key. Once that's done, Ceph should be able to log into both nodes as root without any passwords. With that sorted, let's launch the Ceph command line environment. Running Ceph ADM shell gives us a container preloaded with all the tools, configs and keyrings we need to manage the cluster. From here we can check the cluster status. As expected, we'll see only a single monitor and a single manager service running right now, because the orchestrator is only managing the first node. If we list the hosts, only Ceph1 shows up. Let's add a host named Ceph2 with the IP address 192.168.80.68, and then we'll add the third host, Ceph3, with the IP 192.168.80.69. Now, if we list the hosts again, we'll see all 3 nodes in the cluster. And finally, let's get a quick summary of the cluster health. If we take a look at the output, we can see the status of the 3 major services types: monitors, managers, and object storage daemons, OSDs. Right now, we've got 3 monitor daemons running, Ceph1, Ceph2, and Ceph3, and the quorum has been established. The monitor service is responsible for maintaining the cluster map, which is basically the central configuration and state of the entire cluster. It's often called the brain of Ceph because every other daemon and client needs to consult this map to know the layout and overall health of the system. We'll also see that both the primary and the standby manager services are active. The manager hosts all sorts of plugin modules, like the dashboard, Prometheus, Grafana, the Ceph ADM orchestrator, and more. But notice, something important, there are no object storage daemons running yet. And without OSDs, there's no place to actually store data. That's our next step, setting up object storage daemons. Now keep in mind that each OSD manages exactly one disk or partition. These daemons are the real workhorses of Ceph. They handle storing data, replication, recovery, rebalancing, self-healing, basically anything related to the actual data itself. Let's first check which devices are available for creating OSDs. Alright, each node shows 2 free disks. Perfect. Let's tell Ceph Orchestrator to automatically create an OSD on every host it manages using any available disk. Here available simply means the disk isn't mounted, doesn't have any partitions and doesn't contain a file system. It's just a clean, blank block device. Now, if we check the cluster status again, we should see the cluster reporting healthy and 6 brand new OSDs have been created, one for each of our 6 disks. To get a clearer picture of where the data lives, we can run the OSD3 command. And there it is, 6 OSDs spread evenly across our 3 servers. With this setup in place, the cluster is now healthy, resilient and ready to take on real workloads. To get a sense of Ceph's power, let's explore some of its core capabilities like volume management, thin provisioning, snapshots, cloning and copy on write. In production, these features are usually managed through the CLI or integrated directly with OpenStack via Ceph's native APIs. For this walkthrough, however, we'll use the web dashboard to see everything in action with a clear visual perspective. Let's first log into the dashboard. On the left, we see the major categories: cluster management, block devices, object storage, file storage, observability, and administration. In the Hosts tab, we find the inventory of all hosts registered with the Ceph cluster. Here we can view each host's name, IP address, and assigned role. In this case, we added our nodes via CLI, but new nodes can also be added directly from this interface. Next, in the OSD menu, we can see a list of all object storage daemons. For each OSD, we can see the physical host it runs on, its health status, and whether it's actively participating in data distribution. We can also mark an OSD as out, which prevents new data from being written to it. When this happens, the cluster automatically begins a rebalancing process. Data previously stored on this out OSD is migrated to other active OSDs, ensuring redundancy is maintained. The UI also shows disk size, space usage, and performance metrics. By drilling down, we can access even more detailed information about a specific OSD. Now let's move on to pools. A pool is a logical container used to store data. Internally, data is distributed across multiple OSDs according to the pool's configuration. Let's create one named myPool. Pools define data durability. There are 2 types of pools. A replicated pool that stores full copies of data, providing excellent speed and performance. However, it is less space efficient, commonly requiring 3 times the raw storage to achieve high durability. We also have erasure-coded pools. They are much more space efficient and ideal for large-scale archival or cold storage. A common configuration is 2 data chunks plus 1 coding chunk, similar to RAID 5. This allows the pool to tolerate the loss of any single chunk by reconstructing it mathematically from the others. For this example, we'll choose a replicated pool with a replication size of 3. Ceph will store 3 copies of each object on different OSDs. Note that Ceph does not always use the same 3 OSDs. Instead, data is distributed evenly across the cluster using placement groups and the crash algorithm that determines which OSDs will store the data for each placement group. Replicated pools provide both redundancy and performance, since read requests can be balanced across replicas. Finally, we select the pool's intended usage. CephFS is for file storage, Rados Gateway is for object storage, and RBD is for block storage. In this case, we'll use RBD. Okay, our pool with 3 replicas is ready. The next step is to create a block image, a virtual disk. We need to choose the pool this image belongs to, pick a name, and specify the size. Finally, let's click Create RBD. The image is created as an Rados block device, RBD, the Ceph component that provides block storage. One key feature is thin provisioning. Although we created a 10 GB disk, the pool shows 0 bytes used until data is actually written. This means virtual disks only consume physical storage as needed. For example, we could provision a 1 TB disk, but it would initially consume only a few kilobytes until real data is stored. Also mind that my pool is using 32 placement groups. All are in a clean state, meaning data copies are consistent and available for read-write operations. Note that placement groups don't have a fixed size in megabytes. Each placement group is simply a logical container holding a subset of the pool's data. Okay, we have our replicated pool and our block device ready. Let's put it into use. I have a test server running. It has a 100 GB SDA local disk. What we want to do is attach that Ceph RBD block device to that server. First, we need to install the client-side utilities to connect and manage a Ceph cluster. Then we need two files. The Ceph configuration file that I will just copy from the cluster. There's the ID of the cluster and the address of monitor services. The other file is a keyring containing the credentials for the client admin user. This key is used for authentication and authorization with the Ceph cluster. Client admin is the default administrative user. I'm using it for simplicity, but in production environment, you would create a dedicated user and grant it only necessary permissions. Now we should be able to connect to the cluster and check its status. Okay, we see the cluster is healthy, monitor services are running, and all the object storage daemons are up. Let's list the storage pools. There's our pool. Let's now list block device images that exist within that pool. There's our block device. Let's now connect that Ceph block device image to the local operating system, making it appear as a physical block device. For that, we'll use the rbd map command, followed by pool name and the image name. It did return the block device in the operating system. If we list the block devices, we'll see the rbd0 on the list. This is all possible thanks to the rbd kernel module. We can check what RBDs we have mapped with the show mapped command. Now, we can use the Ceph image as any other local disk. We can partition it, format it, and so on. Let me create a new file system on that disk. Now, let's mount it. There you go. Our server now has a Ceph image, a virtual disk attached. Let's try writing some data. Works. So we know how to create a pool, create a virtual disk called the Ceph image within that pool, and we know how to attach it to host. I'll show that in the next video, but that's exactly what OpenStack Cinder Volume service is doing. When using Ceph as the Cinder backend, every time you create a new Cinder volume, Ceph creates a new image within the pool. This image is then attached to the compute instance and the hypervisor attaches it to the VM. Let's look at another mechanism called snapshots. A snapshot is a read-only point-in-time copy of a Ceph block device image. Ceph snapshots use a copy-on-write mechanism. This means that when you create a snapshot, Ceph doesn't immediately duplicate all the data. Instead, it just creates metadata that points to the original data. This is what makes snapshot creation almost instantaneous. When you write new data or modify existing data after a snapshot is taken, Ceph doesn't overwrite the original data. It writes the new or changed data to a different location. The snapshot still points to the old, unchanged data. This method is highly efficient because it only uses extra storage space for the data that has changed since the snapshot was created, not for the entire original dataset. Let's see that in action. We have this 100 MB test file. Now let's make a snapshot. I will flash the data to disk, freeze the file system, then we just provide the pool name, image name, and the snapshot name after add symbol and unfreeze the file system. I just want the file system journal to be empty. Do you see how quick it was? The read-only point-in-time copy has been created. Let me show you what we can do with it. I will remove our test file. Now let's connect the snapshot to the operating system so it appears as a new disk. As a snapshot is read-only, I will map it in read-only mode. Now let's mount it. Mind that I'm also doing it in read-only mode and also adding the no load option to skip loading the file system journal. If I list our virtual disk, it's empty. We did remove the file. However, if we list the snapshot that was mounted, we can see the file there. That's to be expected, as the snapshot was done prior to removing the file. Mounting a read-only snapshot is incredibly useful for several reasons. Primarily because it allows you to access and inspect data from a specific point in time without affecting the live, actively used volume. In our example, we've deleted the file from the main volume, so we mounted the snapshot from before the event occurred and now can restore the file. You can also use a snapshot to restore the entire volume to a previous state. Let me do that now. I will remove the file one more time, then I will unmount the volume. Now let's disconnect the Ceph block device image from the server. Now we can revert the RBD image to a specific snapshot by issuing RBD snap rollback and specifying the snapshot name. Let's now reconnect the virtual disk, mount it again, and voila, data is there. Next thing I'd like to show you is creating a copy on write clone of a Ceph block device image from an existing snapshot. This process is highly efficient because it doesn't duplicate any data instantly. Instead, it creates a new readable RBD image that is layered on top of the original snapshot. First thing we need to do is protect the parent snapshot, so it can be used as a source for a clone. This prevents it from being deleted by mistake, which would break the child clone. Let's double check it by listing snapshot for our image. Now to create a new readable image from the snapshot, let's run the clone command. As the source, we'll provide the protected snapshot, and as destination, we'll provide a new image in our pool. There you go. Mind that this is a thin clone that takes up almost no space initially and uses the my snapshot as its parent. Also, it's readable. Let me attach it to the server. Now, let's just mount it. Okay, we see the files that were originally on the snapshot. However, this block device is readable. Moreover, it is also very space efficient, as initially shares all data blocks with its parent snapshot, so only the difference, in this case the new file, is stored here. That's the beauty of copy on write mode. That's the method OpenStack uses for creating many virtual machines from a single master image. Last thing I'd like to show you is data resilience. In Ceph, data blocks are distributed across many OSDs to ensure high availability and data durability. We'll test what happens when we lose one OSD, two OSDs, and even an entire node. And you'll see how Ceph keeps our data safe and our workloads running the whole time. First, let's create a test file in Ceph storage. I will use DD and PV to throttle the speed so we can see it happening in real time. This is just a 1 GB file being written slowly so we can watch what happens. Here we can see the file size is growing live. Next, let's watch Ceph cluster health in real time. Here, Ceph-S gives us a health summary. Let's also watch OSD3 in real time. It shows which OSDs belongs to which nodes. Alright, let's simulate a disk failure by stopping OSD1. You can see Ceph immediately marks it as down, but notice, it doesn't start rebalancing yet. That's because Ceph waits just in case the OSD comes back quickly to avoid unnecessary data movement. To actually tell Ceph that this OSD is gone for good, we need to mark it as out. And now the cluster begins rebalancing and recovering, distributing replicas of the missing data across the remaining OSDs. Let's take it further. I will stop OSD2 as well. It's on a different node. This simulates second drive failure. Again, Ceph marks it as down, but no rebalancing yet. Once we force it out, Ceph immediately starts recovery. You can see PGs being re-replicated on healthy OSDs. Now let's simulate losing a whole node. To do that, I will stop OSD4 on node 1. Since this is only a 3-node cluster, something important happens. Let's also mark this OSD as out. Notice, it doesn't rebalance this time. Why? Because with only 3 nodes and a replication factor of 3, each replica must be on a different node. If one node is gone, Ceph cannot create new replicas without breaking the crash rule. Instead, it keeps the cluster in a degraded but available state. That means you can still read and write data, but you have no redundancy until the node returns. Finally, let's bring our OSDs and node back online. And once everything is back, Ceph immediately heals, re-replicates the missing data, and returns to health OK. Our file write still uninterrupted the entire time. So there you have it. Ceph isn't just a place to put files. It's an intelligent, self-healing system whose features, thin provisioning, efficient snapshots and clones, and automatic resilience are perfectly matched for the massive demands of cloud platform like OpenStack. In our next video, we'll bring it all together. We'll install OpenStack and configure its services, Cinder for volumes and Gland for images, to use our new Ceph cluster as their storage backend. Thanks for joining me on this deep dive. Until next time, keep digging deeper.